light emitting diode, and now actually the perovskite solar cell, organic inorganic solar cell. Mohammad Nazeeruddin, he's the man of this topic. And I think he's not just, he did a very deep research and first fundamental research in chemistry of this very amazing material, perovskite material. And he come with a very, very important result, and he make a big progress to get out with all the challenges of this solar cell, the stability of the solar cell. And he don't do just engineering to see if the material or the solar cell is stable, but he go to the chemistry, to the atom. And that's what I appreciate in his research, and I always read his article and enjoy it. So Professor Shamsi Nazeeruddin, he's a professor in chemistry at in EPFL Sion campus, and he's currently professor in different universities over the world. And he is working really now very much on perovskite solar cell. He published quite a lot of good work and very well cited work on perovskite. I think every month I have to update his biography, because there are always new publications, new impact factor, etc. And I just have each index of 171 here, but I think it should be more than that, because it's changed every time. So if someone is dynamic, working very hard, it's always like this. I want to thank him very much to be with us. I know that I'm sure he take his time for something else and he come, and I want to thank him very much. He will talk about the stable and efficient perovskite solar cell and module by compositional and interfacial engineering. And I will not say that much, because he's very well known over the world, and I want just to give him the floor. Professor Shamsuddin, Professor Nazeeruddin, Mohammad Nazeeruddin, thank you very much for coming, and the floor is yours, and we are looking forward to hear you. Thank you.
Thank you for your kind words, Professor Ahmed Anoui. So this is, first of all, I would like to thank all the organizers for putting such an excellent online meeting. I really appreciated your kind invitation. So let me share some of our recent work on perovskite solar cells. I'm working at EPFL now. I'm also working at Atmolite. This is the company where we are producing perovskite solar cells in a gigawatt scale. You will see some of the modules. I also working at Southeast University, which is close to the company. Now, let me come back to the perovskite. The perovskite materials are like a battery materials, very simple composition. You have a salt-like a material, that's a ABX3, where A is a monocation that can be inorganic cesium or methylammonium or formidinium. The B is a metal. In this case, we are discussing only lead 2+, and X is a halide, which can be bromide, chloride, and iodide. And in my talk, I will be focusing only iodide, and the bromide and chloride, they have applications in the light emitting diodes. These materials have a very unique properties. They absorb whole visible absorption spectra from 400 nanometers to 800 nanometers. You can see this one. And then you can change the properties of these materials by tuning either central metal B or halide X. As you can see the spectral responses, how it goes from the complete visible to the UV in the visible in the UV region. So this materials also has a tunable properties. That's a absorption spectral tunable properties. The more important property of this material is the low excitation, small excitation binding energy. The moment you shine the light, you create a carrier charges, positive, negative, they go together. This is called exciton. This exciton binding energy is typically very high. in these perovskite materials, this excitant binding energy is very low. It's less than 30 millielectron volts. That's the reason why most of these materials, they are very efficient for separating charges. So once if you have these materials, how do you deposit these films? There are typically 4 techniques, which I briefly discussed. One is called one-step method, where you combine your starting compounds, lead iodide and organic halide compound together in a solvent like a DMF, DMSO. You spin coat in annihilate at 120 degrees temperature, you form the perovskite film. And the second one is the two-step method, where first we deposit lead iodide, followed by exposure to the organic halide compound gives the perovskite, centering at 120 degrees temperature. The third one is most important for the tandem configurations applications, where you deposit the perovskite on top of silicon substrate by incorporating different crucibles where lead iodide and your organic halide cations. You sublime this under vacuum, and the gas phase you form the perovskite film. The fourth one is industrial application, where you have a first deposit in a wet process, lead iodide deposition, and exposed to the vacuum chamber where you have a organic cation, organic halide cation, it forms a perovskite. So this is the deposition techniques, but there are 2 configurations known in the literature. One is called PIN, and the second one is NIP. The NIP device configuration has a light is passing through the electron transport materials, followed by it hits the perovskite, and the top we have a hole transporting material. Since the light is passing through the ETL layer, the basic condition here is the ETL layer has to be colorless, otherwise it will absorb parasitic the light attenuation. In the other configuration, PIN, we change the charge transport material for electron transport material to the hole transporting material. And here the condition is whole transport material has to be a transparent. So this gives you a lot of design opportunities to tune the properties of this whole transport material. So then the light goes to the perovskite, and on the top we are having whole electron transport material. So these are the device configuration. So let me give you the efficiency. PIN configuration gives you 27%. How does it compare with the silicon solar cells? Silicon solar cells, they have a 27% efficiency. It reached almost the silicon solar cell efficiency. On the other hand, NIP configuration has a 26% efficiency, slightly lower than the PIN configuration. Now coming back to the mechanism, you have a perovskite, you create a positive and negative charges, and then the positive charges diffuses because you aligned the whole transport in such a way that the diffused electrons, positive charges are extracted into the whole transport material and goes to the contact. Similarly, the electrons which are in the conduction band of the perovskite and injects electrons into the electron transport layer, and then you have a charge separation. So here I'm showing a typical example of a cross-section image of perovskite solar cell, where we are having a conducting glass. On top, we deposited electron transport material. This is NIP configuration, and we deposited perovskite, which is typically 600 nanometers, followed by we have a very thin layer of 2-dimensional perovskite. I will give you this in the later introduction. Followed by we have a whole transport material. This type of efficiency, NIP, and the PIN configuration, this will come in the later slides, which gives the silicon perovskite tandem solar cells has an important effect on the high yield, where you reach 34.6% efficiency. Lungi has reported this efficiency. One of the main problem is the stability. So how do we increase the stability of this such a simple composition materials? The answer is going back to the composition engineering, where you try to understand at a atomic level and come up with the additives. So that's the outline of my talk, where we want to engineer the composition, we want to engineer the interface materials, we want to develop charge transport materials to go beyond 26% or 27% to reach a 29% efficiency using such a simple compounds. So one example I'm here showing is an IP configuration, a device configuration I have mentioned before. What we have done in the perovskite composition is we incorporated methyl ammonium chloride. It's a simple compound, methyl ammonium chloride, and another ionic liquid. The name is given here. So what does this ionic liquid and methyl ammonium chloride is doing? When you mix the lead iodide and organic halide compound, they instantaneously form a three-dimensional structure. So here, by incorporating the methylammonium chloride, so we slow down the crystallization process. So what does it mean by the slowing down the crystallization process? So when you slow down the crystallization process, you reduce the defects, and the reducing defect gives you high voltage and power conversion efficiency that gave us 25.5% efficiency. This work appeared in Nature last year. And this is the module efficiency, the mini module. This is the lab scale, which we typically develop, 7 by 7 centimeters square. And the efficiency is using the same composition, 23.3% efficiency. This is the highest for mini module size of this level. The device configuration is shown on the left side, and it's similar as I mentioned. So the take-home message is we have used several ionic liquids and the different halide, different anions, like a BF4 or PF6, iodide, and all these halides, except only the chloride is giving the highest efficiency. That's the take-home message for students. Now I come back to the another interesting, the dopant. So we have used the NN-dimethyl chloride. This is a compound which we have used in the perovskite composition. And then we added dimethylammonium cation in the solution, and it forms a unknown cation. It's a tetrahydrogenium. The structure is shown here. You can see the structure. This tetrahydrogenium cation, it formed, and it gives a very high efficiency, 23.2%. Now, imagine what is this new cation is doing. And the next slide, it shows you what this cation is doing. When you have two crystals of perovskites, and this cation goes in between the two crystals of the perovskite, and it binds to the halides through the hydrogen bonding. So when you bind these protons to the halide iodide, what happens is you reduce the ion migration properties, and then the iodide vacancies formation is decreased significantly. So this way you increase the stability of these perovskite materials as shown here. So it's a 87% you can retain the efficiency of T80 after 4,000 hours stability. And we also measured at 85 degrees, 85 temperature, 85% humidity. And these are the criteria for the perovskite solar cells. And this work appeared again the last year, November, in Science 2024. So the efficiency is shown here. 23.2 is highest for this type of mini modules. Now I come back to the another interesting topic. I'm giving all the information for the students so that they can come up with their own ideas. So some of these additives, when you put into the perovskite, they will precipitate at the grain boundaries. And by having this precipitation at the grain boundaries, you increase the recombination. So in order to avoid this drawback, came up with the design criteria. So the design criteria is the liquid crystals has to be hydrophobic. It has to have some kind of a fluoride so that when there is a defect of iodide, the defects can be passivated. So these are the units which you can see this work is appeared in Nature Energy last year. So here I have shown a couple of examples. Let's take the one example that has 3 fluorides. I mentioned that fluoride groups are important to replace the iodide defect, to specify the iodide defects. And you have a aliphatic chain with the molecule here, which is hydrophobic. And it is a liquid crystal. Liquid crystal at a room temperature, liquid crystal at the temperature where you're processing your perovskite film. Now you put this material in your perovskite solution. When you process the perovskite film, this liquid crystal is uniformly distributed throughout the perovskite because it's a liquid at the temperature of where you are sintering. So this approach has also gave us very high efficiency, 25.6% efficiency in a small cell, and in a mini module, it's a 22.4% efficiency. Most important phenomena is the stability at 45 degrees, 45% room, the humidity, and 85 degrees temperature, 85% humidity. The stability is significantly enhanced. And on the bottom here is the module data. Now I come back to another approach where these perovskites, they have a segregation problem. when we have two types of cations, they segregate as shown on this is a cartoon, just a cartoon. Imagine that you have two cations, they segregate, and then they have segregated patches. Now, how do we get the uniform, the perovskite composition? So here we came up with another ionic liquid, that's a tetrabutyl ammonium trifluamide ionic liquid. By incorporating into the perovskite solution, what you can see is this is on the top, you see the control where cesium is segregated and the lead is segregated, iodide is segregated. By using this ionic liquid, the cesium is uniformly distributed and formidinium as well as lead and iodide. So this is a very interesting approach where you can have a uniform distribution of the cations and iodides. So the efficiencies are in the reasonable, which is not very high, 24.5% efficiency. This work appeared in EES 2024. Now I come back to the PIN configuration, where I mentioned the PIN is a whole transporting material we have to deposit, followed by the perovskite, followed by the ETL layer as shown here. And we have a BCP, this is a buffer layer, and we have a silver. This is a PIN configuration. So to deposit the C60, usually people use sublimation technique and followed by the BCP. But this sublimation technique, when you use the C60, they aggregate on the surface. By aggregating on the surface, you change the energy levels. This is the drawback of the PIN configuration. So what we came up here is we developed a material. This is some kind of organic material which dissolves the C60. By dissolving C60 into the polymer, now you don't have to sublime, you can solution process. This work appeared in this year, 2025. What happens is when you deposit by solution processing, you can eliminate the BCP and then you form a very nice PIN configuration. And that gives you 25.6% efficiency. Now we are eliminating the sublimation process and we are reducing this aggregation of the C60 by using the solution processing method. That's the take-home message. Now I come to the interface engineering. So far I have discussed the three-dimensional perovskites. But if we change the cation size from the small size to a larger cations, which I have given some examples here, and then you form a two-dimensional perovskite. The difference between the two-dimensional perovskite and three-dimensional perovskite is contrasted here, the visible spectra. The visible spectra clearly shows absorption spectra going up to 820 nanometers, whereas the 2D perovskites, they have a spectra only between 400 to 500 nanometers. However, the stability of the two-dimensional perovskite is significantly enhanced compared to the three-dimensional perovskite. So now what happens if you deposit the two-dimensional perovskite on the three-dimensional perovskite? Now here I show the energy level scheme. So you have a perovskite which has a 5.36, it's a HOMO level. And the two-dimensional perovskite is slightly offset by around 100 millielectron volts. So the positive charges are extracted efficiently towards the whole transporting material, whereas the electrons are blocked here and the electrons are injecting towards the tin oxide surface. So what is effectively the two-dimensional perovskite is doing is you are reducing the recombination at this interface. By doing that one, you can see the data, photovoltaic data. So reference sample gives you 109, that's voltage. By using the one of the two-dimensional perovskite, it increases to 1.13, and the second one, pentafluorocation, that enhances further to 1.15. It's not only increasing this OVOC, which is an indication of the reduced recombination, but it enhances the stability significantly over 1,000 hours measured system. Now, are the cations? No, we have several of these cations. So here is the library of the cations we developed, we measured. So in this, the whole diagram, what I just want to show you is the substitution has influence. It can be the fluoride, it can be the chloride, it can be the iodide, but the position, is it in a meta position or para position or ortho position? So if you look at the data, in all the cases, the meta-substituted halide has a significantly enhanced efficiency compared to the blank. So this gives you indication that, imagine that the meta-substitution, why it is giving, the formation energy of the meta-substituted halide two-dimensional perovskite is lower than the ortho and para. And that's the information you can get from this type of studies. I quickly turn towards the charge transport medium. I'm just giving you a few examples so that people can think of their own new materials. So here is the typical charge transportable spirometad, well known in the literature. So what we have done is this charge transport spirometad is not very stable because it has to be doped, because conductivity is low. The dopant induces the instability. So what we have thought is, can we migrate the positive charge over the larger distance? So we increased the pi conjugation, and then we made this molecule with the dopant, and we reached similar efficiencies like a spiro. It's fine, but still it's a doper. Now, can we do the without doping? So without doping, how do we do that one? So the idea is you have to stack the whole transport materials vertically on top of perovskite. To stack the whole transport material vertically on top of perovskite, you need some kind of a planar structure. So here we have taken a planar core, and this planar core, it stacks. And here for the first time, without any dopants, as synthesis molecule, it gives over 24% efficiency. So the idea here is you don't have to have a dopant if you stack the molecules like liquid crystals one on the top. So this is the self-assembly monolayer. This is the molecule is well known in the literature for the tandem configuration, which the people are getting very high efficiencies. However, the linker between the head group, the donor group, and then the anchoring group is a flexible one. So we developed a non-flexible donor bridge between the donor and the anchoring group, and this gives you high efficiency compared to the flexible bridge. Another interesting, the self-assembly monolayer is shown here, and this one also gives very high efficiencies. I just skip because of the time. This is a the efficiency is 25.28%. It's not significant, but it's a new molecule. Now I come back to the electron transport material. So here I just want to spend, so when you have a TiO2 or tin oxide or mixed layers as electron transport materials, now you can see the stability of these perovskite solar cells. If you have only TiO2 as electron transport material, the stability is decreasing significantly. Well, if we have a TiO2 and tin oxide deposited on top of TiO2, or pure tin oxide as electron transport material, the stability is significantly enhanced. Why this is happening? It's because when you shine the light through the ETL side, there is just some certain portion of 3.5% of UV light is there. The UV light is exciting the TiO2, and this excited TiO2 is eating the perovskite, thereby it's delaminating. So here is another approach we came up with, increasing the stability of these materials by incorporating the sulfonate groups. So this work will appear in advanced materials. This gives you the ETL layer for the first time. We have reached over 26% efficiency by using this type of ETL layers. So here we developed a nanocrystalline TiO2 materials. The difference is the conductivity when compared to the colloidal nanoparticles. TiO2 nanocrystalline materials enhanced significantly. As a result, you see the enhanced fill factor, this property I have not mentioned before. The fill factor increases, and the increased fill factor enhances the power conversion efficiency. And also you can see the 9 cells module, it gives a 10 volts the voltage, and then the efficiency is 22.87 of this module. Now, quickly turn to attract the attention of the students. So the tandem configuration is very important because it increases the efficiency for the same geometric area, and reported efficiencies are 34.6% efficiency. So in the tandem, we have two configurations. One is called a 2-terminal, another is 4-terminal. The 2 terminals are separated mechanically. They put together on the one on the top, whereas the 2 terminals are monolithically integrated on top of silicon solar cells. And this type of configurations, you can also have a NIP when you take the N type of silicon substrate or PIN. So here also you can have a PIN or NIP configurations. Both are working. So this is the work from Christobalev's groups, where they deposited conformally by sublimation technique. So when you have a silicon wafers, You have a silver, the pyramids, and the perovskite is conformally coated on the top of this one. I just want to show this. This is not my work. Now I come back to the progress in the industry. So we are having the gigawatt line where we are producing large panels of these modules, and they are installed for the charging facility. And here is the outside the measurement system, where measured over the 5 months period, the efficiency output energy is compared to the silicon solar cells slightly enhanced. It's because of the negative temperature coefficient. Silicon solar cells, every degree temperature increase, you have a decrease in the efficiency of 0.4%. And whereas perovskite solar cells, they don't have a negative temperature coefficient. So this is our factory where we install the perovskite modules as a boundary, and it is a 7 megawatts line where it's providing the electricity to the plant gigawatt line. And I just want to give the conclusions here, and then just me show the group members, and then followed by the project fundings, and then the institute and the group members. And thank you for your attention. I will be happy to answer your questions.
Thank you very much, Professor Mohammed. Now we will open for the discussion for 2 or 3 questions. So please open the floor for the audience if someone he want to ask, and give him also open their microphone. And here Mohammad Nazeeruddin, he will answer. Thank you. So if any questions in the audience, please go ahead. Just leave your hand electronically or show up your photos and talk in the micro. So I am talking to the audience now. If someone he has any questions to Professor Nazeeruddin. So apparently no one is there. If you allowed me to ask you, Professor Mohammad Nazeeruddin.
Yes, please.
Yeah. It's business questions, because for the fundamental, it's be very difficult. Do you think now that solar module will be in the market? Because I saw that there is one company, I think NG called, I guess, or what? There is a Chinese, I guess, Chinese company.
Yes.
And they make a very, very big module, and they want to know if now it's confident if the market is confident for this technology, which always deal with the stability. What do you think?
I believe this material is quite stable, provided if you manage interconnections and the sealing. So these are the 2 very important parameters of everybody has to come up with their own materials. If you master this sealing technology and interconnects, and they are quite stable. And we in this factory at Atmolite, we produce gigawatt lines 2.4 by 1.2 large panels, all automatic, and you get a 17% efficiency coming out of this module. Okay. 2.4 by 1.2 panel.
Yes. So the organic side of the module, it's not a problem.
The material side, we mastered the materials properties to stabilize, but the sealing is very important. I'm not underestimating the sealing properties and interconnections. Okay. That's a laser scribing, P1, P2, P3, this laser scribing, and then the sealing. These are the 2 important parameters. Who wants to develop this? This is a important topics.
Okay. So is there any question in the audience?
Zainab is raising her hand.
Yeah, Zainab Akash, please go ahead.
Hello.
Hello.
Thank you very much. Hello. Thank you very much for the very interesting presentation and for all your efforts. I want to ask you a question about the industrial perovskite. I tried very hard to have the specifications to the simulation. Been very, very hard to get them. I called as I'm very interested in this futures solar cells, but for me it was very hard. So I just want to know if Professor Nazeeruddin can help me in this way for just the simulations, because as you know, in Morocco, the possibility, a lot of means to make a very advanced research. So just apply simulations.
Yeah.
So just before, my understanding that you want him to help you in the simulation. That's what I
Yes,
understand.
because I tried to have the specifications of the perovskite solar cells manufactured by a company in Poland, but it was impossible to get them. I tried all the ways. Even in China, I tried via the to have them. It was impossible. So I just wanted to make some simulations, and it was for me impossible. I said when I said for simulations, as you know, it's just low level, and even for low level, it was impossible in Morocco. So if Professor Nazeeruddin can help me to get some specifications about the industry,
Yeah, the question is clear. The question is clear now. So
Yeah.
please, Mohammed, Professor Mohammad Nazeeruddin, have you something to say?
Yeah. What I would ask is, if you can send me the email address, just send me an email.
Okay.
You can see my email is given on the top. Let me
Okay.
just, yeah. So my email is here. So you just write to me what you want, and then
Okay.
probably to assist you for your simulations. This is not a big issue because it's not a